Welcome again to the NPTEL course on storage systems. In the previous class, we were looking at how message ordering, if not done well, can create complications, and today we will look at this in slightly more detail. I should first mention that this is a slightly tricky subject, and there has been a lot of let us say, a lot of research work done in the last 20 years or so, and there has been a lot of let us say controversy on some aspects also. For example, the people who build systems, they might have a certain model of how things should work, and then if people who are more trained in the mathematical side of things, they come and look at it, they might have a different perspective on what is going on. And there has been an interesting exchange of ideas or even controversy among these two communities, and this area is one such interesting area. It is so there is a lot of subtlety and depth in this area, so I will try to mention some aspect of it in this particular talk today. So let us look at, again, the whole issue is about message ordering in the context of failures, and how if you can somehow make the job of the programmer easier. So that is the whole idea. Okay. So let us first make some definitions. First of all, we can have what is the notion of a static and dynamic membership in a group. What is static? There is typically a mapping between some hardware or some such entity and processes that are restarted on failure. So the typical model is that it is restarted on failure. The dynamic situation, you start a new process, it joins the system, and then it leaves the system on termination, failure or disconnection, it never comes back again. Again, if somebody else comes in, it is a new process, it is not the old thing that was restarted. Okay. So in this case, it is always somewhat static. If something dies, it comes back again with its same ID in some sense. Here, the IDs are keeping on changing, okay, if somebody comes and goes. So that is one part of the one definition. There is also something called dynamically uniform, which is a slightly more subtle concept. Let me explain what this is. Okay. If any process performs some action, all processes that remain operational also perform it. What does that mean? I could do something, and then if I end up doing that, then whoever is in that group should also do it, irrespective of whether I live or die. Okay. So sometimes it is very critical that this happens. For example, in a commit kind of protocol, if one of them is committed, everybody else also should also commit. Again, let us take a slightly different example. Suppose you have a parallel file system, and different processes are doing some computations on different portions of the file. It is basically a parallel file system. The file is a very long one, let us say it is about 10 gigabytes. There are 24 processes or 25, whatever, 100 processes working on that one 10 gigabyte file. Each one has got a certain domain in which it is operating. If one of them updates one part of it and dies, it is important that other processes, irrespective of whatever happens, they also should update it. Otherwise, what will happen is that you will have some updates from this guy, but no updates from other guys. So it is some kind of mixture between some updates made by this party and no updates by other parties. So those things are somewhat problematic. So what is in dynamically uniform? Again, I will show it by an example, by diagram. Suppose you have some sender S, it is doing a multicast. So it is going to A, B, C, D. Okay. Now, S sends a multicast and it dies. Similarly, A gets it, it does whatever has been done and dies. And this B, C, D, they are surviving. Our interest is that if A gets something and does something because of receiving that message from S, it is very important that B, C, D also actually act on it. This is what they call dynamically uniform. Irrespective of what failures, the minute a message is delivered to one party, it is absolutely critical that everybody else also sees it, even if the whoever has got it die before other parties get the message. Okay. So again, in spite of crash at sender S, if message delivered at A, it will be delivered at BCD. Okay. So for example, that's the reason why commit protocols or Paxos, etc., they have this model. If somebody has committed somewhere, doesn't matter if that party is not living, you also have to commit. Similarly in Paxos, if somebody has, in the consensus kind of algorithm, right, if somebody has accepted this and there is a majority and that has been accepted as the, for that particular round, as the agreed upon value, everybody else also should do it irrespective of who lives and who dies. Okay. So this is a critical thing in many situations, but there are other situations which is what is called non-dynamically uniform. If I send a crash, and we can even assume there is some kind of partition, I sent some stuff to this guy, there was some partition that came along, therefore this messages somewhat never made it to any of these places. Okay. So these applications here never receive that message, and it's okay in those kind of situations to not, the server not get the message and nothing really matters. Okay. For example, if you are an air traffic control system, somebody is giving updates of the current aircraft that is out there. This could be display stations A, B, C, D. The fact that the new updated view of what aircraft is being seen is not available B, C, D is not really serious an issue. Okay. Whereas if I am issuing money from an ATM, for example, and it has debited the money from the database or whatever, but that ATM itself has a mechanical malfunction, right? It doesn't give the money. That's a bad situation, right? Basically, if in case it has committed there, irrespective of what happens, somebody has to know that this ATM malfunctioned and it will actually keep track of it and again try to deliver it, the money to you somehow. If it does its job of debiting it from the database, your account, but does not take care to ensure that you get your money, then something is wrong. Because you can see all these are distributed in space and time. Something is happening in database somewhere else. Something is happening at the ATM, the mechanical contraption that is giving you the money. And if it's a dynamically uniform system, then if something has happened in the database, it will happen also at the mechanical contraption of ATM where you are using it. Okay. It cannot just assume that the database failed. Okay. And none of these fellows were, none of the ATMs were, or the ATM was informed about it. You can keep quiet. Okay. That doesn't work. Okay. It's not a sensible thing. Okay. So that's where, so this is a dynamically uniform system, which is a slightly more complicated system. Okay. Basically because there are external visible actions that are critical. Okay. So, okay, there are two or three issues here. This is slightly different from a commit also. Okay. I mentioned that dynamic uniform and commit are similar, but there is some difference there also. Okay. So, if you look at this particular diagram, if some of these guys die, it's okay that these guys don't see it. Okay. Whereas in a commit protocol, because you are assuming that they are going to be restarted, okay, they have to be, it's important that the message actually goes to them also. Okay. So, basically in a dynamically uniform system, what is guaranteed that if a party does something, right, all processes that remain operational, that's important. Okay. That's the difference between commit and dynamically uniform. Okay. There is some subtlety here that we should remember. Okay. Basically what it means is that one process has done something, whoever remains operational from that time onwards should also do it. Okay. Whereas in a commit protocol, all of them have to do it, irrespective of failures, because all of them have to commit. So if some of them fail, they have to restart, again they have to set the system right and then do it. Okay. That's the difference there. Okay. So in a sense, you might say dynamic uniform is somewhere between the model of commit and the one which is the previous model, the different from the dynamic one and the one which is the commit one. Okay, there is some difference there. Okay, okay. So that's one. Okay. So in a non-uniformly dynamic system, the states and actions of processes subsequently fail discarded. Okay, operational part of the system defines the system. Okay, so this is slightly more easier. So just imagine what has to be done in the case of dynamically uniform. What you have to do is, if any time a message goes to, for example, let's say there are nodes. There is a node 1, 2, 3, 4. The process is A, B, C, D. So a message goes to node 1. Now what you have to do for dynamically uniform is, you have to ensure that these messages are received at 2, 3, 4. They are buffered. They do some kind of a protocol saying that all of us received a message, whoever is surviving. Okay, and once that is done, then then at this point you deliver it. And BCD, having got those things earlier on, they will also have saved it persistently. So in case A has actually, it has been delivered to A, the process A in node 1, then it is possible for us to make sure that node 2 also delivers it to process B, and node 3 gives it to C, and all those who actually survive after this was delivered at this point. Okay, that means that there has to be a lot of activity that has happened before you can deliver the message to A. The process is A, B, C, D. Okay, that means first you have to send the messages to all the nodes. All of them agree that they have received a message. All of them agree that they can store it in a stable storage of some kind, right? And then once one of them has delivered it, other parties also can assure that it can be done. Okay, otherwise it's not possible. So in a non-dynamically uniform system, you don't have to do all these things. Okay, because what you say is, whatever is remaining, it's okay, because we can do delivery for whatever part of the system that remains. Okay. So similarly, for the same reason, there are two types of what is called failure atomic multicast. Okay. One is the dynamic uniform, the other one is non-uniform. What is in the case of dynamic uniform? If it is a case that suppose you send a message M, okay, and if P delivers this message M, okay, that means it is guaranteed, because of dynamic uniform, that in any future execution, because there is some future after this, right, because once P has delivered to M, there is something else is going to come after that. It is guaranteed the minute it has delivered to M, it knows that in the future execution, in which a set of processes remain operational, okay, there is some set of processes that remain operational, okay, okay, there is a guarantee that the delivery of M, okay, among that set of processes also is guaranteed, okay. So that is basically dynamic uniform protocol. Whereas in a non-uniform protocol, okay, if P knows that if both the sender of M and P crash, okay, M may not reach its other destinations. The fact that it has been delivered in P, but if P as well as the sender both crash, okay, it's perfectly okay that the message M does not go to other guys. Whereas here, the important thing is that the minute one process at one node, the message M has been delivered, then it is somehow the system has to do something, whatever has to be done, to ensure that it goes to all other remaining operational processes. Okay, that's a difference. Okay, there are some situations where this is important, there are some situations where this is important. Okay, so typically, if there is some kind of persistent state that has to be there and has got externally visible actions, this is important. If there are no seriously important externally visible actions, this may be okay. So there are a few more definitions. there is a notion of what is called reliable broadcast or MCAST. Sometimes in some places we will call it a cast instead of referring to broadcast or MCAST, that is multicast or broadcast, we will refer to it as in general as a cast. That is why we are calling cast here. Okay. Now, what is we have to decide what is the correct, what is the correct process? The correct process is one which has not failed. Okay. That means it's all, we are now taking care of, we are talking about what is called fail stop processes. That means when they fail, they stop, they don't lie, they don't do Byzantine things. Okay. So, what is the correct process? The correct process is one, it has not failed. So, if I just say a process, it may mean it is possible that during whatever we are doing, it may fail. Whereas, if I say it is a correct process, it means that whatever I am talking about, it does not fail during that time. Okay. So, what am I saying? Here what we are saying is, in this reliable broadcast MCAST, we are only saying about correct processes, that is that which do not fail during this particular operation. If a correct process casts message M, all correct processes eventually deliver M. Okay. That means that none of these things, the guy who has sent it or the guys who received, none of them have failed during this particular process, during this particular cast. Okay. If a correct process delivers M, all correct processes eventually deliver M. Okay. This is the guy who started it, the guy who has, one of them has delivered it. Okay. He is also a recipient. If one process receives, other process also receives. Okay. Okay. For any message, every correct process delivers M at most once and only if M is cast. Okay. Okay. Again, this at most once is also not easy. Okay. I think you remember that in NFS, you can't really do this. Okay. That is why you need to have some logging going on there also. Okay. This is not trivial because you might retransmit. If there is a message loss, you will retransmit, and it is possible that the ACK did not go through, but the message went through. So, you can actually get more than one copy of the message. That means that somebody on the receiving side should keep track of it and drop the second one. Okay. So, this also not trivial. Okay. Okay. So, this is the case with, we are only discussing about correct processes. Just like in the case of the dynamically uniform situation, we can also have a uniform model corresponding to this cast. Okay. So, this differs in with respect to correct or faulty process. Okay. So, we are talking now about faulty process. Again, if you remember our previous discussion, commit protocols versus consensus protocols, right? They differ with respect to failures. Commit protocols, irrespective of failures, you really have to ensure that those parties that have failed actually reboot again and do something. Whereas in consensus protocols, we don't care about those processes that fail. Okay. We are only talking about correct processes there. Same thing here also. So, that is what this was the case. Whereas in the case of uniformity, you are saying, you can see the difference. Here we say a process delivers M. Whereas here we say if a correct process, that means that this process can deliver M and die. Okay. Whereas in this case, because the minute I say correct process delivers M, that means this process lives through this particular broadcast or MCAST. Whereas here, the process can deliver M and then die. So, if one party succeeds in delivering it, all correct process eventually deliver M. That is all those guys who survive, right, for after this guy is delivered, they actually deliver M. Okay. So, there is a small difference between these two things, and it turns out that there are, if you are modeling all these things mathematically, all this matter seriously. Okay. That is where there has been a lot of controversy in some of these issues. Again, I will illustrate some other details. Okay. So, given this kind of situations, we need a model by which we can program our systems. Last time we looked at some issues which create complications when you are trying to program this kind of systems. So, there is one model which is called the view synchrony model. I introduced it briefly last time, and Kenneth Berman from Cornell University and his students, they developed it first. and there are other models at various other research groups have come up with. I am going to follow mostly the Burnman kind of model. Okay. So, in this particular talk, in this particular lecture. Okay. So, what exactly are we doing in this case? Here the idea is that somehow when messages are sent, you have to ensure that the messages are sent and received in the same view. What is a view? View is some notion of what all the processes that are up and running. Okay. And anytime a failure occurs, you are going to view that as a separate event, which ensures that previous messages all are delivered by that time, and then this failure event occurs, and then again messages are sent. So, in a sense, failure events somehow separate out the message sent previously and after. Okay, it's some kind of barrier. Okay. If you are able to do that, then programming of this kind of system becomes slightly easier. Okay. The whole idea is failure events are some kind of barriers. Now, in principle it is not possible, because while a message is going on, you can also fail, right? The message is in transit. So, what you have to do is to find a way in which you somehow delay the delivery of messages in such a way that you get this particular perspective. Real systems are different. Idea is to somehow move around things a bit, so that you still have the same notion by which message is sent in a particular view, it is delivered in that view, and then the failure occurs, and then messages have again start taking place. Okay. So, that is basically what it is. Okay. So, what is the requirement? Each process at each time instant has a unique view of membership of the group. That means, when a failure occurs, atomically somehow everybody knows that that failed party is no longer part of the group. Okay. This is sort of instantaneous. Of course, there is nothing instantaneous. It has to be managed somehow, so that this kind of view is possible. Processes that proceed together 2 consecutive views deliver the same set of messages between these views. Okay. Again, what is a view again? I mentioned already what it means. It means a coherent idea of all the processes that are up and running. Okay. For example, I know that 4 processes are up and running, they are P, Q, R, S. Then one of them dies. Then let us say R dies. Then there is P, Q and S. After this failure event, everybody else in P, Q, S knows that there are only 3 processes. Okay. Okay. That is basically what it is. And if processes that proceed through 2 consecutive views deliver the same set of messages between these views. Okay. And there is some ordering between this also, we will talk about that later. Okay. That also has to be possibly be followed. Okay. What is critical about this view synchrony model is each message associated with a view. So, each message is associated with a view. Okay. Every message is associated with a view, and all send and receive for a message occur at processors with that view only, in that view only. Somehow you have to fake it somehow so that this happens. Very critical. Okay. Send and delivery events considered as a single instantaneous event. Somehow you have to find a way of making it happen. Okay. We will come to this soon. Okay. Basically, these are all abstract or impossible ways for it to happen, but we will going to take this and try to come with a similar actual realistic model. Okay. So, essentially what we are talking about is this part, all send and receive for a message occur at process that view. Okay. Virtual synchrony is the actual model, and this basically uses this view synchrony kind of idea to support a execution model, so that it is easy to program. Okay. And this is defined in terms of a unrealizable close synchrony model, which I am going to talk about next. Okay. What is this close synchrony model, and how is that used to define virtual synchrony? That is what we are going to look into. What is the close synchronous execution model? First of all, I should mention again, repeat one more time, this is infeasible. Okay. Multicast delivered to all group members as a single reliable instantaneous event, okay, which of course makes it impossible. Okay. It is reliable communication, it is not like TCP streams that can break unreliably at different times as seen by different people. So, it is not like TCP, it is reliable communication. So, if the group expands, okay, membership of group fixed at the deliver of a MCAST. That is, suppose I am trying to send a message, multicast, before I send it, I have a membership of group. I know exactly who all are part of the group. Okay. Delivery ordering of concurrent messages. What are concurrent messages? There is no way in which you can order the messages. There's only at the most a partial order amongst messages. Concurrent messages, there's no way to order them. Different multicasts, distinct and ordered same. So if there are two different multicasts which are distinct, they are ordered in the same way across all of them, all the processes that receive it. This is a delivery ordering of related messages. Suppose there is some relation between messages. Okay, that is, one is there is a reason why they're related. One happens first, it does something because of that, because it's causally connected to the second one, right? Then something else happens. So this is a causal connect, related messages. Then I have to ensure that the messages that are received, that same causal order is possible. Okay. So again, we will go into this in greater detail later, but this is, we are interested in a particular abstract model where either the messages are concurrent and therefore they have no relationship amongst themselves, okay. But whatever the messages are there, they will be received by all the parties in the same way. If they are related, then I also have to make sure that they are received in the same causal order. Okay. The state transfer happens at well defined points. For example, when a new member comes in, it's the group goes through a new state. Okay. Failure atomicity. What we are going to say is that the MCAST is a single logical event. Okay. Similarly, failure reporting through group membership changes that are ordered with respect to multicast. Again, any failure that happens is some kind of a atomic event. Okay. So we want to ensure that all these MCAST or failure events, they are seen as atomic events. Okay. So that you can decide how to order them. Now these things definitely, some of them very difficult to achieve, but if you have something of the kind, it makes programming easier. Okay. So what is virtual synchrony? It is basically the same as this, but you can permit asynchronous executions, which has to be same as something similar to this, okay, but and it has to be indistinguishable. I think it's similar to the way that when you're talking about serializability amongst transactions. What are we talking about serializability in transactions? They're actually concurrent. But what we say is two sets of transactions are serializable in case there's this, the two, even if executed concurrently, they have the same effect as some order, some arbitrary order in which the two transactions are executed in a serial manner, right? Similar to this also, we say a virtual synchrony is something which is, look at a closely synchronous execution models of the various events that are taking place. You are saying that a virtual synchrony, it's a virtual synchrony in case you can show that whatever way you reorder things, it is corresponding to one, some close synchronous execution. Any one, it doesn't matter which one. Okay. So again, just to recapitulate, if you look at serializability of transactions, what are we doing there? Actually, the transactions are concurrent. So they're actually reading and writing data possibly, which are shared at the same time, right? And so your concurrent transaction manager will do something to ensure that locking etc. will take care of that problem. But suppose we say that there are two transactions. Now it is serializable, these two transactions are serializable in case you can order them as A followed by B, transaction A followed by transaction B, or transaction B followed by transaction A. Okay. So the effect of the concurrent execution should be either A followed by B or B followed by A. That's all that matters. We don't specify it has to be A comma B. It doesn't matter if it's A or B followed by A. Okay. That's what is equal to serializability. Here also same situation. I want the situation to be in such a way that I can reorder things in such a way that whatever way I reorder it, it should be corresponding to one close synchronous execution. Okay. So, because of this, I can drop the notion of instantaneous. Okay. As long as I am able to show that this virtual synchronous execution can be seen to be equivalent to some close synchronous execution. Okay, I am done. Okay. So, permits asynchronous executions for which there exists some closely synchronous execution indistinguishable from the asynchronous one. Okay. So, that is basically virtual synchrony. Okay. Again, those process groups in which failures or messages are ordered that way, they are called virtually synchronous process groups. Okay. Again, let us try to see some of the differences here. Okay. Now, various types of models are possible. You have transactional serializability, but as I mentioned earlier, in transactional, you focus on isolation of concurrent transactions, and there is persistent data and rollback. Okay. The focus is on isolation of concurrent transactions. That is where serializability comes into picture. Okay. Both virtual synchrony and transaction order, right, they are basically order based execution, because there is some kind of ordering you have to ensure. Okay. What is different about virtual synchrony is that there is direct cooperation between group members, failure handling and dynamic reconfiguration to make progress even when partial failures occur. Okay. This part of it is not really part of the serializability aspect, that is independent. Okay. Even commit, for example, the protocols we looked at, it is some kind of a reliable multicast. We are not talking about concurrent transactions, etc. We are talking about agreement amongst a group. There is no concurrency as per se here. Okay. That is why this is different from this. Okay. But we are also, just like transactional, we are also concerned about durability. If you look at multicast delivery, let us say if you are talking about IP multicast, so the guarantees are much weaker. Whereas in the case of multicast, the way we are talking about, whether it is dynamic uniform or whether it is non-uniform, we are giving slightly stronger guarantees. This IP cast kind of multicast, for example, that is far less, much less guarantees are given. Okay. Now, we can define what is called a group membership service. Okay. Now, there are some subtleties here also, because one of the problems about the FLP result is that the Fisher-Lynch-Patterson result is that you can't figure out if somebody is actually extremely slow or dead, right. So, at the most you can suspect somebody being not live. Okay. So, there are some complications because of this. Again, we looked at the split brain problem as well as the Mexican shootout, that also will crop up here. So, the behavior actually depends on how the failures or supposed failures actually play themselves out. Suppose a process P suspects that process Q is faulty. Okay. Ideally, what you might want to think is, if P itself remains in the system, Q will eventually be excluded from it, right. P is suspecting something, and if P itself is not faulty, then if Q is indeed faulty, then Q has to be taken out. Okay. But the problem for us is that P itself might be excluded. Again, we are talking about the Mexican shootout at same situation. Both P and Q might be excluded because each suspect the other. Okay. As we discussed that time also, system as a whole prevented from making progress if less than majority that participate in the previous system view remain operational, because sometimes what happens is that some quorum is not established, therefore you can't really make any progress. Okay. Basically, you really can't decide what to do in those kind of situations. The quorum is not there. You just have to muddle along till something happens, so that again quorum is established, right. So, instead of this particular type of description, people have people have tried to model it carefully. They have decided that instead of this particular model, if P remains, they said if P suspects failure of Q, then Q eventually square system unless P itself is. So this turns out to be a slightly better spec than this one. So various theoretical models have come up where they try to use this kind of models. As I mentioned, this area is full of complications, and lot of different theoretical models have come up where you make mild changes here in the axioms, you might call it, and different kinds of things have come out from it. Okay, let's just look at some of the issues again. It's like basically our problem is partitions, right? If there is a partition, what I would like to ensure in these protocols, progress should happen only in the primary component. Suppose you are an air traffic control system, various parties are trying to get the aircraft into reasonable situations. Part of the system, one part of it gets disconnected. So what we would like to do is that there should be progress only in the primary component. There should not be inconsistent actions taken in two different partitions, because that can be extremely risky. So what we are saying is that somehow we have to decide which is the primary component. So in non-primary, at the most it can do safe actions. It means it does not update anything. At the most it can read things. It can only do what is called safe actions. Suppose there is a process P which is ejected from primary. Then, as we discussed earlier, you can have what is called a split brain problem if P does not know that has been ejected. If it does not know it is ejected, it can go ahead and start updating it. Instead of indulging only in safe actions, it can start updating things and can get into problems. There is also the views should be causally ordered. Again, we will talk about this later. If the partition heals, you may want to merge the two partitions. Again, this is a complicated thing about how to merge partitions if they heal. And this is something which also many people have faced. If you have what is called, when you develop software, you have various control version systems, and when you might also have the merging operations there. Similar issues also crop up here also. You have to make the state of the system consistent. There has to be merging operation also. One critical thing in this kind of systems is that, again, we discussed also in context of Paxos. If there is a new primary component because of some failures, there should be some overlap with that of the previous one. This is also critical. Now, you will find that you need something like a 2-phase commit or 3-phase commit protocols to make all this happen. So, I will just go into some details about that. So, what is the, basically we are trying to do membership. We are trying to figure out who is there, who is not there. Because some failures have taken place, I am going to try to figure out who is out there. In the first phase, list of add delete events sent to all, including coordinator, and the acknowledgements or anybody who gets it should act. In the second phase, the coordinator waits for majority of acts. If majority acts you get back, you commit updates including failures that happened during the first phase. Again, you can see this is also will introduce certain complications, but we will assume that some of this can be handled. And all update new view. If majority do not respond, wait till communication restored or run a special protocol. Must prevent a new primary component in which coordination not part, because this in principle is impossible, but you should try to ensure that the new primary component, if it is not part of the, if the coordination is not part of the new primary component, then it creates certain complications. Okay. So it's better to prevent it. Okay. I'm not going into detail about this part. Okay. So in 3-phase commit, if you are going to have a new coordinator, there's an election here if coordinator fails, and you informs at least majority about coordinator failure. Okay. Because a new coordinator informs that there has been a coordinator failure, collects acknowledgements and current membership informed from all, proposes new membership doing the whatever new events have taken place, add or deleted events. Okay. And then it goes back to, essentially you can again restart from 2-phase commit. Okay. So basically our problem is either the majority may not respond or the coordinator might fail. If the coordinator fails, then you get blocked, right, just like in the 2-phase commit situation. Okay. If you want to avoid the 2-phase commit blocking, you have to elect a new coordinator, and basically for the same reasons we discussed previously, you again have to propose a new membership, and then you have to restart the protocol again and see if you can get agreement again. Okay. So you can go back and forth between 2-phase, and the way Berman has described it, he basically combines 2-phase commit and 3-phase commit, so that you get some interesting optimizations. Okay. So what are the various requirements in the, I think let us summarize requirements here for virtual synchronous of system views, right. Every view is basically some idea about exactly who are all living, all responding. Initial system view at system start, subsequent views differ by the addition and deletion process. Okay. Again, these are all axiomatic things which are needed for mathematical modeling. Only processes that request to be added to the system are added. Only processes suspected of failure or that request to leave system are deleted. Okay. Majority of processes in view I must acquiesce in composition of view I plus 1. So some kind of quorum is there. Without quorum you don't do. Okay. Starting from the initial view, system view, subsequences of a single sequence of system views reported to system members. Each system member observes a subsequence starting with a view in which was first added to system and continuing until it fails, leaves the system or is excluded from the system. Okay. If process P suspects process Q of being faulty, then the core service, right, basically the group membership service, is able to report new views. Either Q will be dropped from the system or P will be dropped or both. Okay. So basically the idea is that if this particular system is live, okay, again this is another condition. Okay. The core GMS service is able to report new views. Because of our FLP kind of results, this is also not possible to guarantee in all cases. That's why there is an if here. If the core GMS service is able to report new views, either Q will drop from the system or P will drop or both. In a system with synchronized clocks and bounded message latencies, any process dropped from the system view will know within bounded time. Again, we will see all this within bounded time, etc. Again, all the while since we started talking about NFS and consistent problems, you notice that almost all the important guarantees are given in terms of some eventuality will happen. And here we are talking about assuming that there is a synchronized clock. Okay, so that's why we are able to say within bounded time. If you don't have synchronized clocks, you can't give any of these guarantees. And actually it turns out synchronizing clocks itself is a very hard problem. I think we discussed it, mentioned briefly, but I will mention it in slightly more detail in the next slide. Okay, this actually is an interesting problem that in many common situations, synchronized clocks are actually impossible. Okay, let's just look at how that is. Okay, suppose you have two nodes P and Q with two clocks. Let's say the clock P is ideal, so the time is equal to T, and clock Q is the one which is slightly off. So it's actually, since ideal, this is actual true time. So this is basically A times T plus D. A is the skew and B is the offset. Okay, instead of going at 45 degrees, it is going at a slightly different angle, and also there is an offset. Now suppose I make the critical assumption, delays are asymmetric. Okay, that is, from P to Q the delay is D1, from Q to P is D2. Okay, now what do we have to decide? Okay, basically if I want to synchronize clocks, I have to decide what A, B and D1, D2 are. Okay, so you do any set of network packet exchanges. Okay, it has been shown that it's impossible to do so. Okay, basically it turns out if you draw the diagrams and write these equations corresponding to when something was sent and something was received on the other side, and reason about it, you can actually get some kind of matrices, and the matrices, it turns out, for determining 4 of them, you should have a rank 4 matrix. It turns out to be rank 3. Therefore, it's not possible to get these values. Okay, but what is interesting is that if you either drop this asymmetric situation, or if you are interested only in the round trip delay, then it's feasible to determine in this model. Okay, so when we talk about this within bounded time also is slightly problematic. Okay, because in principle, this assuming synchronized clocks is too strong. Okay, it is actually not a feasible system in many situations, because the delays are often asymmetric. Why is it asymmetric? Because you could be between certain either bridges or routers and various things, and it may be that the paths you take are asymmetric. Okay, so it is not really guaranteed that both are symmetric. Okay, and it's even more so, suppose you are in a wireless situation. It turns out that your message going in one direction depends on the condition of the channel, radio channel. Okay, so therefore D1 and D2 could be quite different. It depends on when you send it. Okay, so all these things are in practice quite reasonable, the fact that delays are asymmetric. Therefore, if that's the case, then what we assume here is actually also problematic. That means that typically this also you can't assume. So that's a desirable set of things. So as I mentioned, it's not easy, but let us proceed all the same, okay, because our idea is to come up with engineering solutions. So for that, if you have a group membership service, you can have the following kind of API. What does it do? You can say join PID callback. It returns basically the time you joined and the list of members. Okay. So callback is called when membership change. For example, the PID joined. So if some new guy comes in, he is informed to update its use that okay, new guy has come in. What is interesting about this is idempotent. If join fails, can issue it again to some other JMS server. Again, what we are assuming is there is not the group membership service is actually, it has to be a highly resilient service in itself, right? So this itself should have multiple nodes, and if one of them fails, somebody else should be able to take over. Okay. So what I am saying is that in case I make this call and I get a response saying that it's not okay. Okay. we can again reissue it because it's idempotent. Okay. Same thing with leave. I can keep trying to leave till somebody says yes, you can leave. Okay. What is monitor? Again, you want to find out if a particular PID, something happens to it. So I'm basically saying, this is a process I'm interested in, and then please monitor it. Is telling the service. Okay. And so in case something happens to this, the PID fails, then GMS itself calls back this callback on using the PID as the parameter. Again, this also has to be designed idempotent, so that in spite of whatever happens, just can repeat it one more time. Okay. And there will be some other, because we are talking about, there's a core set of services nodes which are actually giving you the group membership service, and that itself has to be replicated, and if one of them fails, somebody else is there to look after it. So that if it's idempotent, it doesn't matter if something fails, you can just repeat it. I will briefly introduce ordering semantics today, but in the next class we will go into in greater detail. Okay. Now, so far we talked about how to handle failures, okay, how to ensure that the failure looks like atomic, so that I can, is something like a barrier, then all the messages before and all the messages afterwards. That's what we are trying to do. Now, the question is about sending the message itself. You can either have no semantics whatsoever, let it happen whatever the way it happens. It can happen in the FIFO model. The process casts M before M prime, that is the same process. Okay, I am sending. Okay, I send M before M prime. Okay, then no correct process delivers M prime before M. That means that everybody also should get M first followed by M prime. Okay, that is because I am able to order the things at my side, everybody else is able to order it at their side also in the same way. Okay. There is also something called causal. If cast of M precedes M prime, no correct process delivers M prime before M. Now, this precede itself, there is a technical definition for it. Okay. What is the technical definition? Basically, we do it in terms of events, and that events basically can be used to define the precedence relation with respect to messages. Okay. So, what is this? This again, Lamport has defined this particular model. What exactly is this? It's a very familiar model. The process executes both E and F in that order. That is, E is, I execute E first followed by F. That's in my system, in my node, okay, I execute E first followed by F. Therefore, E is before F. That's very non-controversial, right? There's no problem because I'm doing it in the same node. I do E, then I do F. Therefore, E should be before F. Suppose it's across nodes now. This is a definition with respect to across nodes. What is it? E is the cast of some message M, and F is the delivery of M at some process. That is, I sent a message. E is the thing which is initiating broadcast or multicast at my node, my node for example, and F is the delivery of M at some process. Then I say that E precedes F, that is, sending has to precede the delivery, receiving. It's a very simple model. Okay. Okay. Or there is an event H such that E precedes H and H precedes F. That is, I do something, there is somebody else who follows in the precedence relationship with respect to using one of these or recursively. There is something which comes after that, and that itself is before F. Therefore, E is before F. Okay. That's the reason, that's what we call saying that if an MCast or a broadcast M precedes M prime, the definition is this. In case this is not, this particular precedence doesn't apply, they are concurrent. There is no way to order them. That means there is no way in which they could have ever been causally connected to the other. Therefore, they are actually concurrent. Okay. So, this is the order. So, basically in causal what it says is that if in some way you can show that M precedes M prime in the causal definition, this using this order, this one, you have to guarantee that no correct process delivers M prime before M. Okay. So, the other models also I will continue with. I just want to introduce the kind of ordering that also has to be looked into as part of this whole definition, okay, and then we will go further detail in the ordering part of it in next class, and hopefully conclude it with respect to all the required things with respect to failures as well as method, okay, in next class. Thank you.